Good morning, students. Now we are going to class number 4 of unit 3, that is in group theory, for the second BSc students who are studying third semester for the academic year 2020 and 2021. Okay, students, previously we have learned 10 theorems in the normal subgroups, that is unit 3. Now we are going to theorem number 11. What is that? If M and N are two normal subgroups of group G such that M intersection N is equal to singleton E, then prove that every element of M is commutes with every element of N. Previously we have proven that a normal subgroup and a group and a subgroup both are satisfying commutative law. Now he is asking that M and N both are normal subgroups and their common point is, their common element is E only, that is identity element only. M and N both have only one common element, that is E. Then prove that every element of M and every element of N, that means each and every element of M and each and every element of N must satisfy commutative laws. That is commutative law or abelian law, whatever it may be, the same one. Now for that, now I am writing in the proof that what is given that M and N are two normal subgroups of group G such that M intersection N is equal to singleton E. That means there is a common element in between M and N, that is only E. E is the only element in both M and N. There is no other element which is lying in both M and N. Okay, right. Now we want to prove that small nm is equal to capital Mn, where small m belongs to capital M, small n belongs to capital M. N is in an element in capital N and small m is an element in capital M. Means the elements of M, capital M is small m and capital N is small n. There must be satisfies the commutative law in between these two elements, that is Mn is equal to Mn. We want to prove like this. Okay, right. Students, we know that small m belongs to capital M and capital M is in G, big set G. We know that capital M and capital M both are in G because these two are in G. Okay, right. And small m belongs to capital M and M is contained in G, means the small m belongs to G and N belongs to N. And N is normal subgroup of G, means by inverse law N inverse belongs to N. Small n belongs to N. By inverse law, N inverse is also belongs to capital N. Now M belongs to G, N inverse belongs to N, and N is normal subgroup of G. By the definition of normal subgroup, here big set is G. M N inverse M inverse belongs to N. M N inverse M inverse belongs to M by the definition of normal. Students, all of you want to know that all of you must learn the definition of normal subgroup and understand the definition of normality, and you have to learn it very thoroughly, and after that only you can understand whatever it may be the theorem and whatever it may be the proof you have learned in these 10 theorems, and this is the 11th theorem. All of you studying? All these theorems are proved by the definition of a normal subgroup only. So all of you must understand the normal subgroup definition very well to prove any theorem in this unit. Okay, right? All of you understand that? Right. Now N belongs to N. We know that small n belongs to capital M. This M N inverse M inverse M N inverse M inverse belongs to N. I have written like that. The same one I have written here. Belongs to N. And N is normal subgroup, means subgroup. Subgroup means closure law exists. What is that? Closure law exists. That means the product of these two elements belongs to N. That means N into M N inverse M inverse. N M N inverse M inverse belongs to N. Okay, right? Okay, right. Now I am writing that. What is that? Small m belongs to capital M. What is that? Small m belongs to capital M. And M is normal subgroup of G. M is normal subgroup of G. Then what happens? N, M, N inverse, M inverse belongs to M. Okay, students? Many of the students get doubt in this bit. just you can follow the above one, and similarly we can do like this, because I am explaining very with orally. I am explaining orally that M is lies in M. Is it right? N is lies in N. N is lies in G. What is, where is N? Capital N is in G. That means small n is in G. By the normality means N belongs to G, M belongs to M. M is normal means N, M, N inverse belongs to M. N, M, N inverse belongs to M. And also M belongs to M. M is subgroup. That means M inverse is also belongs to M by inverse law. M inverse belongs to M. The first three elements M and N inverse belongs to M. By closure law, NM, N inverse into M inverse belongs to M. Okay, students, I will explain this elaborately if you in our WhatsApp group, if you call to me, or in our classroom when you came to our classes directly in physical classes, that is which are going to be conducted in the next week. Okay, students. Okay, right. From 1 and 2, we can say that what is 1? N, M, N inverse, M inverse belongs to N. The same element is that N, M, N inverse, M inverse belongs to M. That means the same element lies in M, and the same element is lies in M. That means these elements, that means this same element belongs to M intersection M, M intersection N. But we know that M intersection N is equal to singleton E. That means there is only E is the element in M intersection N. Here another element is there, that is in M intersection N. That means this becomes E. This becomes E. That means N, M, N inverse, M inverse is equal to E. Okay, right? Now N, M, N inverse, M inverse is multiplying with M on both sides, with right side with M, E, M. Now M inverse M becomes E. N, M, N inverse as it is. M inverse N becomes E, E, M as it is. N, M, N inverse, E is identity means N, M, N inverse remains, and E, M means E is identity means M remains. N, M, N inverse is equal to M. Similarly, we multiplying N on both sides, we will get Nm is equal to Mn. That means the small n belongs to capital N, small m belongs to capital M, and each element of N, each element of M having the commutative law. This is called abelian law. That means every element of M commutes with every element of N. Thus the theorem was proved. That is theorem number 11, proof was over. Next, we learn the definition of simple group. A group G is called simple if it has no proper normal subgroups. What is that? A group is called a simple group if it has no proper normal subgroups. That means it has only improper subgroups. What is that? In a group, if it has only improper subgroups, then it is said to be a simple group. Okay. Now we go for the theorem number 12. What is that? Prove that every subgroup of prime order is simple. That means it can be asked another way also. We know prove that every group of prime order is improper. Is improper. Or has only improper normal subgroups. Improper subgroups. You can get the question like that also. Okay, right? What is that proof? I am taking that G is a group and its order is P, where P is a prime number. All of you know that what is the prime number? What are the prime numbers? 2. 1 is not a prime number. All of you know that. 2, 3, 5, 7, 11, 13, like that. These are called the prime numbers. What is the property, basic property of these prime numbers? There is no factors for these prime numbers other than itself and